How y'all doing? This is going to be the last lecture for stats midterm, section 5.1, 5.4, which has a lot of things to do with discrete math if you're doing computer science. But we haven't done in discrete math the probability of a set. It just has like some discrete syntax, but nothing too crazy. So we'll head straight into it. A sample space. So you have something called a sample space, which is, you can think about, in other words, if you've done discrete, it's your universe, which is basically all the options you have. So for example, let's take a die that has 6 faces. That would be 1, 2, 3, 4, 5, and 6. So sample space is basically the total number of events that can occur. And then to find the probability that some event from the total number of events is happening, is you want to take the number of events that you want to get and divide it by the total number of events. So if I want to see, well, what are the chances I get a 3? If I roll the dice and I get a 3, well, that's 1 out of 6, because I can only get 1 3 out of 6 events. And so if there is 2 3s, however, and I'm like, well, what are the chances I get I get a 3 out of 6, but there's 2, so that'd be 2 out of 6. My chances is there's 2 out of 6 chances that I get a 3, because there's 2 of them. Like, I don't know how else I could word this, but I hope that kind of gets you. The probability of an empty set, so this is an empty set, which is, S equals like just nothingness. The probability of nothingness is just 0. Now we do have some syntax things. We have a, B, this is and, well, in other words, this is actually or. So you can think about it as everything in A or in B. So if the element is in an A or in B, put it together. So if my set was x1 and my B was x1, x2, what is this set going to be? Remember, we said it's an element that is in A or in B. So x1 is in A or in B. So this is going to be x1. x1. What about x2? x2 is in B, so we put it in. Because remember, it doesn't have to be in both. I said it has to be either in one or the other. Now, just like A intersect B, this is for this one. It's an intersect. This is and. So this means the element has to be in A and in B. So x1 is in A and in B, but x2 is not in A and in B, and therefore, so we don't put it. One thing is, again, this is make sure it's no duplicates. A complement is basically not A. So if I am doing the intersection, let's see, B and A not, so this is equivalent to this. Okay, so what I'm saying here, it's B and not A. And so here, so x1 is in A, so therefore I can't put it here. x2 is not in A. So that's how you do it. If I were to do it, I think we're going to go over it in a bit. For the above example, we listed the sample space of a rolling, well, you guys don't see the above example, but we have a dice that has 4 sides, not 6, 4. So it's 1, 2, 3, 4. And let's say the probability of the following events. So the sum of 4 or less is basically you roll a die twice, and the sum has to be either 4 or less. So remember, your S, which is your sample space of everything, would be 1, 1. And then you have, 2, 1. And then you have 1, 2. And then you have 2, 2, and so on until you get every combination. But remember, here, you see, you can't have duplicate as in 1, 2, because this is different from 2, 1. Okay, so keep that in mind. But they are still possibilities that you have to put in. They're just not duplicates, since they're the different order. Anyway, so that their addition, so 3 plus 1 is 4. It can't be more than 4. So if you roll the first one, you get a 4. You roll the second one, you get a 4. that can be within the set of A, because this adds up to 8, which is a sum is 4 or less. The second set, which is B, is the second roll is 2. So you roll it the first time, the second time gets a 2. And you want to get every combination. So you roll the first time, you get a 1. You roll the second time, you get a 2. That's one combo. You roll it once, you get a 2. You roll the second time, it's a 2. That's second combo. So you want the second roll is always to be a 2. And you have 4 combos for that. So now, what I'm saying here, by find the probability of A union B, remember union is an OR, which is an element has to be either in A or in B. So what is the chances I roll my dice twice and the combination I get is either one of these or one of these? No duplicates out of my sample space. So remember, if earlier we were like 1, 2, 3, 4, 5, and 6, and I was like, what are the chances I get 3 out of the sample space? You said, well, there's only one instance, so that's 1 out of the total instances, which is 6. So this one, how many instances are there on the top? Well, we have 1. Here, let me remove this. We have 1, 2, 3, 4, 5, 6, 7, and 8. Now, if you think why I didn't count these, because no duplicates. These are here and here. So that's why I didn't put them in. So there's only 8 I can get, right? Because remember, the union is you're saying everything in A and everything in B, no duplicates, divided by, what is my sample space? How do you find your sample space? If you have 2 options, which is here, we're rolling it twice, 2, it's 2 to the number of combinations there are. So since we have, the dice has 4 sides, there's 4 combos, so it's 2 to the 4, which is 16. That's how many combinations we can get. And so this is 8 divided by 16, which is 0.50%, right? The Venn diagram of this probability, so this is how you do a Venn diagram. You have one circle, you have second circle. This represents our B, this represents our A. The box is our S, which is everything in between. And so A mu B, the probability of that is we're looking the probability of getting everything within here. Okay? Finding the complement of A is basically we're saying, what are the chances I get A? So you're going to be like, well, what's the probability I get A? Well, A is 6, right? There's 6 instances of getting A. So that's 6 out of 16. Then what's the probabilities of getting anything but A? Well, if the chances of 6 over 16, which is, if the chances of me getting this is 37.5%, well, the answer is 0.375. I just converted it quickly. So if the chances of me getting A is 37%, what are the chances I don't get A? Well, that would be 100% minus my 37.5%. And those would be the chances I don't get A. That's basically what it is. The addition rule of adding 2 sets, so if I do A plus B, this would equal A set plus B set minus A intersect B. Why do we minus it? Because if I take this set, and I have this, and I first, I take A, so it's this section, right? And then I add it to B section. What I just did, as you could see, is I added the middle section twice. And that's why we minus 1 middle section. This is the intersection. A and B. It's something that is in both, which is this middle area. That's A intersect B. So we're minusing it once because we're adding it twice. Okay, so the probability is the same thing. So the probability of A, I believe it's just union. So, oops. So the probability of A and B equals the probability of A and the probability of B minus the probability of A intersect B, because we're adding that probability twice when we do this. So that's why we minus it. Okay, mutually exclusive events is basically saying, so the Venn diagram is you're basically saying my two circles have nothing in common, they are disjoint. And so what they're saying is this is written as A and B equals, so when I say A and, oops, and share, A and B equals an empty set. Why? Because remember, there's nothing in between. When you have something that looks like this, the area in the middle, it's your A intersect B. But since there's no area in the middle, that means their intersect is just nothingness. That's how you know they're disjoint. Addition rule for mutually exclusive is that if they are disjoint and you add their probability, then you don't minus the intersect. Why? Because there's no intersect, so this goes to 0. That's why we don't minus it. Okay. Now we are gonna get into a little bit trickier things. Let A and B be two events with the probability at B being 1 to 0. So this is a conditional probability. We're saying that A occurs given that B has already occurred. So when would we need this type of probability? Let's assume this. The probability, so let's say A equals person who's hungry. And then B is person buying pizza. Oops. Buying pizza. Okay. So if I want to say, well, what is the probability somebody is buying pizza assuming they're hungry? So let's actually flip this around just so we're within the context of this. So let's make this B. Let's make this A. Oh, I just did the same thing. Lol. So this is going to be A, and this is going to be B. So what I'm saying is, what is the chances somebody is buying pizza assuming they're hungry? So already assume they're hungry. So if somebody's hungry, what are the chances they're buying pizza? Dude, I'm starving right now. I could actually feel some pizza. But, so that's basically what conditional probability is you're basically assuming one thing happened. You're saying the chances of something happening assuming the second thing has happened. And so why do we divide? So remember, what we would be doing is getting the probability that somebody is hungry and buying pizza. Buying pizza. Right? That's the probability of the top. Is that both of them? We're saying and, right? So first we're going to get the probability that they're both happening, which is somebody's hungry, somebody's buying pizza. We're not saying the person who's buying pizza is hungry. We're just saying the person buying pizza and the person is hungry. Then we're going to divide it by the probability of the person being hungry. Because remember, we're trying to find the probability of A. That's ultimately our goal. Is we're trying to find the probability of A. But we're not trying to find just anyone buying pizza. We're being specific. We're saying, I want to find the probability of A assuming they are hungry. And so what we do is we'll find the probability that they're hungry. So we'll find the probability of everyone that's hungry. Then we'll find the probability that everybody's buying pizza. And then we're going to take everybody that's hungry and buying pizza. Okay? Then we are going to remove the probability. We're going to divide it by everybody that's hungry. So this, you can think about it like this cancels out. So it gives you the probability of A, assuming B happened. Okay? So I hope that explains it. Alright, boys. And so you could do it the other way. Just make sure you know what you're dividing by. So you're dividing by the one you don't want. So if you're looking for the probability of A happening, then you're dividing by B because you want B to cancel out. And then if you want the probability of B happening, then you would divide by A because you want A to cancel out. And that's about it. The top always stays the same, it's just the bottom. Because if you're doing the probability of A intersect B or the probability of B intersect A, it's the same thing. Okay? Example, a certain die is used to produce aluminum cans, blah, blah, blah. You don't really need to know this. We just know the population is 1,000, so we don't have to add all these up. Basically, somebody is manufacturing some cans, and the cans can either be narrow, so all these numbers under narrow, they're either okay or they're too wide. That's for the diameter. And then for the length, they can either be too short, which is everything here is too short. And so basically, the sweet spot they're looking for is this section, where the diameter is okay and the length is okay. Alright? A can is sampled at random from this population. What is the probability that the diameter is okay, given that the can is too long? So remember, they want the probability, so you want to read it from what you want. The probability that the diameter is okay, so we say let A be diameter okay. Diameter is okay. And let B be the other one, which is too long. So what we're saying is, I want the probability of A. That's how you read it. What probability do you want? Remember, it says, what is the probability of the diameter is okay? And we said diameter is A. So I want the probability of A, given B happened. Okay, so that's how you read it. So therefore, the top will always stay the same. The bottom, you want to cancel out what you don't want. Remember, I want the probability of A. So this is going to be what I don't want. Okay? And so, what is the probability of A intersect B? So, let's see. A intersect B is the probability that it's okay and it's too long. So, the probability that the diameter is okay, which is this section, right? But I want it to be too long. Oh wait, I might have messed up. Oops. It's supposed to be this way. So this is the diameter is okay, and then too long is this section. Oh shit. I hate teaching sober. As you can see, even the way I'm talking is lazy, but it is what it is. So we're looking, what are the chances you get this out of the whole thing? And so what we're going to find, we're going to do, well, 25. What's the chances I get 25 out of the whole thing? So that's my probability of A intersect B. Then I'm going to divide it by the probability of just B happening, which is that it's just too long. And that would be 2 plus 25 plus 13, which is 40. Divide by 1,000. And so what happens here is I'm going to have the probability of B cancel B. And I'll be left with just the probability of A happening, assuming B already happened. So you'll just do this math and you'll get some answer. Find the probability is a can is too long, and also find the probability that a can is too long given it's too narrow. So the probability of a can being too long is just P of too long is B. So that would just be the probability of B, which is just 40 divided by 1,000, right? Then they're saying also find the probability that a can is too long given it's too narrow. So you'll do the same thing we did here. I'm not going to go through that. But what you'll find is they both give you, so given, let's say, S, given the probability that is too long, so actually we want B, given S, which is too narrow. You'll find that both of these will be the same. I believe it's like 0.4. Since they're the same, that means, and this is where we're going to go, it means they are independent events. That means if the can is too narrow, has nothing to do with if it's too long. And why is that? So you see, if you go to your data and you look at it being too long, well, you'll take this 40 and you divide it by all the cans. Okay? Now, what are the chances? So this is the chances. It's too long out of 1,000. Now, what is the chances it's too long out of all the narrow options. Because remember, we're saying, given it's narrow, what are the chances it's too long? Well, that would be 2, right? This is the narrow. That would be 2 divided by the whole thing, which is 38, 48, 50. And the chances of you being too long out of all the narrow and the chances of you being too long out of the whole thing just happens to be the same combo. Like, if this was a 3, then I don't think it'll be the same. Or if this was, let's say, 10, then it's not. It just happens to be the chances, you like the numbers, when you add them up, they happen to be the same. And since they're the same, your chances are the same. And that's all it says basically. That's when they mean, like, when the event is independent of the other. Now, how do you know they're independent? Is if you get the probability of their intersection and you get the probability of each of them individually and you multiply, the numbers are equal. If they're equal, that means it doesn't matter. And that's what we just proved up top, is that it's the same thing. So what else we got? A group of 200. So here is basically they're showing the same proof of, if they're the same. See it right here. This one shows dependence though. So what I'm saying here is, what is the probability of some A happening? Don't even worry about the question itself. But let's say the probability of my A happening is 50% of the time. Okay? And then I say, well, what is the probability that my A happens assuming M happened, which is what the question says. Assuming M already happened. If this number is also 0.50, that means the probability of my A happening clearly has nothing to do with the probability of M happening. Because we just saw the probability of A happening on its own, which was 50%, and then we're like, okay, let's take into consideration M. If M happened, what are the chances I get A? And it's also 50. So that means M doesn't even matter. But if this was, let's say, like 0.3, then you'll be like, oh look, M actually affected my outcome, which means it is dependent. M actually does matter. And so that's basically what it is. So how do you see independence and dependence? So independent, these are the rules basically, which is what I just explained. These and this is the exact same, it's just vice versa. This one is what we just learned up. Where is it? Nope. Right here. If you get the probability of your intersection and you get the probability of one times the probability of the other, and they're both the same, this also says it's independent, which is the two events don't matter. And that's about it for this section, really. It doesn't get all that hard. The next thing I'm gonna do, I'm gonna go over all the homework questions, and I don't mean by go over is I'm gonna do all of them. I'm gonna just skim over them, and I'm gonna select the few that are different. Then what I'm gonna do is I'm gonna mix all them together. Because with probability, for example, you need to identify whether a function is discrete or it's binomial. Remember, binomial is a discrete function, but binomial has certain parameters you have to meet. For example, the probability doesn't change, the chance is the same. It's either true or false, yes or no. So you have to know how to identify binomial. So you can't just do a unit for binomials and be like, oh, okay, I understand binomials now. That doesn't work, because a big part of binomials is identifying it's a binomial. And so that's what I'm going to do. I'm going to make a selection of all the good homework questions. I'm going to mix them together. Then I am going to make a video solving them. And you guys should do it. And then if you don't get a question, watch me do it. And that should prepare you to get 100 on the midterm. If that doesn't get you 100, I don't know what will. And then after that, I believe there is a midterm review. So if I do have enough time, I'll do that as well. Okay, ladies and gentlemen, have a great day. Oh, where's my record? Okay, there you go.